Discussing about potential and potential due to point charge and potential energy, and then we discussed about potential conservation of energies, problems based on the conservation of energy. So in the today class, we are going to discuss about the potential due to the continuous charge distribution. So we in the previous classes we discussed only about the point charge distribution. Now today we are going to discuss about continuous charge distribution. So almost these derivations are same as that of our electric field derivations, similar to that of electric field derivations, and such a potential calculations we already did in the gravitation topic. So almost all the derivations are same. So here I am going to just explain how to derive all those expressions. And so after watching this class, you have to derive all those derivations by yourself. So don't copy any derivations from here. That means while watching the class, just listen the class and derive all those expressions by yourself and verify the final expression. Just that's it. And so here we may derive the potential directly by taking a small element and then by integrating. Technique is there here. Technique is nothing but we know the relation between E and V, and we derived the expressions for electric field due to the different objects there. So now we can use that E expression to calculate the potential expression. By using that EV relation, we already did some problems in the last classes, previous classes. So if you know the electric field, from that you can calculate the potential. So now we are going to use that method also. So some derivations I will explain by using that EV relation, and some derivations I will explain by direct integration method. So generally, now here let us see here. So when you are considering this small element here, whenever you are taking a continuous charge distribution, and if you want to write the potential at this point here, so first we take a small element like this. So then by potential due to this small element at the required point we can write here. So because if you are taking a small element, that is nothing but it is we can assume that as a point charge. This is a small element in the sense. And so then dV is equal to 1 by 4 pi epsilon naught dq by r we can write here. Right? And now this dq value. Now we need to substitute the dq value here. The dq value we need to substitute according to the given problem or according to the object. So like if it is given as a one-dimensional object. So for one-dimensional object, we write this dq value as lambda into ds. So where lambda is charge per unit length and this ds is the length of the small element here. If the object is one-dimensional object. So if the object is like a two-dimensional, like a plane or disk surface or any plane surface is given, then we write this dq value as sigma into dA, where sigma is nothing but surface charge density, that means charge per unit area, into this area of the small element. If the object is a three-dimensional object, like a volume distribution of a sphere, so then this dq is given by rho into dV, where rho is a charge per unit volume charge density, and dV is the volume of this element. So just according to the given problem, then just we need to substitute this dq value. So dq expression is different for different types of objects there. If two-dimensional object is given, so for two-dimensional object we need to substitute. If it is three-dimensional is given, so for three-dimensional object we need to substitute the dq expressions there. Then after substituting the dq expression, then just we need to write the total potential here. So the total potential we can write just by integrating this term here. So 1 by 4 pi epsilon naught into dq by r. So then actually potential calculations will be somewhat easy when compared to that of field calculations, because if it is a field calculation, so after writing this dq expression, we need to verify whether field due to all the elements are producing in the same direction or they are producing in the different directions here. But in case of potential, as it is a scalar quantity, so there is no such a need here. Just by writing for the small element, then directly we can integrate that. We can integrate that expressions there. So that is a general procedure to write this potential due to the continuous charge distribution. So we write a small object, and then by integrating that for the small object, we can take this integration of that small element expression, so that you will get the total potentials there. So in general, this is the common point here. So we need to mention this potential at infinity. Generally, we consider as the reference for that. So with that reference, generally we calculate that, and there are certain exemptions for this also. So let us see, in the further derivations I will explain them. What are those exemptions there? So now let us see our first one-dimensional object. So I am going to explain this line of charge first. So here I am taking this electric potential due to a charged rod of infinite length. So infinite line of charge we are taking here. So this is the infinite line of charge having this uniform linear charge density lambda. And so now our point is P is a point here at a distance of r from this rod here. And we know the electric field expression here. The electric field due to this infinite line of charge at this point we can write as lambda by 2 pi epsilon naught r. And so now we know the EV relation. So then EV relation is nothing but dV is equal to, actually our relation is nothing but, we write that expression as dV is equal to, we can write this expression as minus E bar dot dr bar. And so then according to the given limits we integrate this. So according to the given limits means here at infinity we consider the potential as 0. And at distance r we are taking that potential as v here. So that is the thing we need to write here. So that expression we are directly writing here. So then directly we are writing this expression here. So v is equal to minus in integral of infinity to r e bar dot dr bar. And so now here we are substituting that e expression from that, and then that lambda by 2 pi epsilon naught into dr bar, and both of them, that means dr bar and r bar will be, e bar and dr bar will be in the same direction, so that that angle will be 0 degrees we are substituting here. And so next here the integral of this constant, if you write outside lambda by 2 pi epsilon naught r, then you will get ln r, that means 1 by integral of dr by r you will get, so which is nothing but ln r, limits are from infinity to r. So then here now we can observe this ln r minus ln infinity you will get. So that means ln infinity means it is undefined. That means again infinity you will get. And so for this you should remember that the potential due to this line of charge at any point, the absolute potential is generally not defined. We can't define this potential at this point here. So if you are defining the potential here, then this will be the problem. So then if you are taking a reference at that point at infinity, then you will get that potential at that point is also infinity you will get. So in general we define the potential difference between 2 points there. In case of a line of charge, we can calculate the potential difference between the 2 points, but exactly the potential at a point is not defined. Or sometimes they will give like at a distance r from this at a distance say a from the line of charge, they will take the potential as 0. Then let us ask, they may ask the potential at a distance b from this line of charge at some other distance. That means instead of taking the infinity as a reference, they may ask by taking another point as a reference. So accordingly, which is nothing but simply potential difference calculation only. And so now let us see this. So that means here we are taking that assumption only actually here. So the potential at the point VQ is taken as 0, which is at a distance of R0 from this. So we are taking such an assumption there. At some other point we are taking that potential as 0, or you may take some finite value also, then it becomes a potential difference. So next let us say this. And so now we are defining the potential difference between those 2 points there. That means now here we are taking, suppose this is the line of charge. So on this line of charge here we are taking one point here, and this is another point we are taking here. Suppose you may take one point as P here and another point as Q here. That means we are taking the 2 points like this. And so now here this P is at a distance of R from this, and this Q is at a distance of R0 from this. So that is what we are taking here. So then similar, again same derivation, same as that of our previous calculation here. The only difference is this limits we are changing here. Instead of taking from infinity to R, we are taking here from R0 to R. So that is the only difference here. So then again you will get minus lambda by 2 pi epsilon naught into ln R by R0 you will get. And this value we are writing as Vp minus Vq is equal to minus lambda by 2 pi epsilon naught into ln R minus R0 you may write. And if you consider like potential at the point Q as 0, then you can write potential at the P value you can write by using this expression here. or otherwise if the just the potential difference is required between P and Q, so you can leave this expression here itself. That means this if the potential at Q is not taken as 0, just we need the potential difference, then what I am saying is this expression you can leave here itself. That means I can write this as so I can write this as Vp minus Vq is equal to lambda by 2 pi epsilon naught R into, so I can write this expression as ln R naught minus ln R. So we can leave this expression like this. So if they gave that potential at one of the point as 0, that means if they gave some reference, that is nothing but we call as the reference point. If they gave that as a reference point, then you can take this VQ value as 0 and then we can write this expression here. That depends on the given conditions. So this is a potential difference expression here. So the potential difference expression, you can take this as a potential difference expression here. So potential difference between the 2 points. So whose that separation is R and R naught from this. So that is a potential due to the line of charge calculation. That means infinite line of charge calculation. Is it clear? So that means you need to remember that potential due to infinite line of charge at a point is not defined. So by taking some reference at some other point other than infinity, or we can define the potential at a point, or we can calculate the potential difference between 2 points there. So at infinity reference is not valid for this line of charge, infinite line of charge. Now let us see in case of finite charge distribution. That means if you are taking a rod of finite length. Now let us see how to derive that expression there. And so now let us see this. So electrostatic potential due to a line of charge of finite length. See, in finite length there are two cases will be there. So one is for calculating like an axial point here. Axial point in the sense along the length of the rod, or some equatorial point, like that means perpendicular to the length of the rod. So first here I am taking this a point at a distance r from this one end, and at the distance that means along this axis here. This case we now first we are going to calculate here. And listen this, actually this expression is given as one of the previous question. Directly this expression asked in the 2013 JEE mains. That means just they calculated, they asked the potential at a distance of r along the length of this wire here. So that means here what we are assuming is Q is a charge distributed uniformly on this a rod of length L. So we are calculating potential at a distance of r from this. So for this what we are taking is we are taking a small element of this here dx at a distance of x from this. So our procedure is, after taking the small element, our procedure is we write the expression for this potential due to the small element and then just a simple integration. So then first we are writing this dq, how much charge is present in this element here. So charge on the small element. So that we can write as q by L. Q by L is a linear charge density lambda into dx, length of that element. And so now here the potential dV value we can write it as, so dV is equal to 1 by 4 pi epsilon naught into dq by x. So that is the potential because our point is at a distance of x from this element here. So now this is the potential due to the small element. Just we are integrating that, then you will get the net potential at this point here by substituting this dq value here, just integration. So again here you can observe that you will get this dx by x integral of. So that means now here integral of dv is equal to integral of dv. So 1 by 4 pi epsilon naught integral of q by L into x into dx from r to r plus L. So let us see the limits here. This r value varies from this r is varying from this limits, or that means limits we need to take from, if you are at the near end then it is r distance, and if you are at the farther end of the rod then it will be r plus L. So our limits will be like that. So that limits we need to take here from r to r plus L, and just again logarithmic function you will get and just substitute these values here. Then this is the expression for this potential due to this line of charge along its length here at a distance of r from this wire. So this previous directly this expression they asked in the previous mains question. And so next let us see how to calculate in case of at a distance, perpendicular distance. I think you can easily understand this. No need of again repeatedly explanation here, because we did a lot of derivations, such as similar derivations there, right? And next let us see at some other point here, like suppose if this is the case 2 I am taking here. So now here this is the line of charge finite length L, and same let us consider this lambda is the charge density, or you may assume that Q is the charge distributed on this. Now we need to calculate electric potential at this point P here, so which is at a distance of y from this perpendicular distance y from this rod, right? So now from this, in order to calculate this, our procedure is same. So our procedure means we take a small element. First we take the small element. We write the expression for electric field, electric potential due to that small element, and then integration. By integrating that, you can calculate the total potential difference there. A total potential of this particular point we can define there by taking infinity as a reference. And so now our procedure is same. So first I am taking this potential, this element which is at a distance of x from this point here. And so now this point we are taking as some symmetrical point here. That means this point from the midpoint O, we are taking a point at a distance of x from this where we are taking this here. And so now this is our element is x. We can take this as dx, this length of this element, and which is at a distance of r from this. So by using this right angle triangle, you can write this small r as under root of r square plus y square you can write. And so now dv is equal to 1 by 4 pi epsilon naught dq by r, right? Now dq expression. Dq means we know already this is lambda into dx. So lambda into dx by r. R is nothing but x square plus y square whole power 3 by 2. Now just we need to integrate this expression here. So the integration of that expression, to integrate this expression, so this if you integrate, then you will get this expression. This lambda by 4 pi epsilon naught is a constant value. So that we are taking as constant, and we are writing it outside. So the remaining variable term is this one. So dx by under root of x square plus y square we need to write here. And that is our smaller value. And so now the limits we need to take from this minus L by 2 to plus L by 2. That means limits we can consider here. If you are taking this as one end as minus L by 2, other end will become plus L by 2 here. So minus L by 2 to plus L by 2 we are taking here. So that is the limits what we are considering here. And then the integration, actually the integration of this function will be, you will get the logarithmic function here under root of dx by x square plus y square is equal to log base e here, log base e x plus under root of x square plus y square you will get. And this integration will be easy for you if in mathematics if integration topic is completed for us. So here you need to remember it as a formula here, integration formula. And if once if in mathematics the integration is completed, then this calculation will be very easy for this. Almost all the derivations will be very easy for you. And so then just we are applying that formula here, then you will get log base e x plus under root of y square plus x square minus L by 2 to plus L by 2. And then just we need to substitute these limits here. That is minus L by 2 to plus L by 2 limits we need to substitute instead of this x. Then just if you substitute these expressions, you will get lambda by 4 pi epsilon naught into log base e L by 2 plus or minus under root of L by 2 whole square plus y square minus L by 2 plus under root of L square plus y square L square plus y square, sorry, L by 2 whole square plus y square. So that is now expression for potential due to this finite line of charge at some symmetrical, that means at some equatorial point we can say. So now this is the expression for this potential due to this finite length at some equatorial point. So that is about the line of charge in the different cases regarding this line of charge here. And now similarly now we can take this the another simple object like a ring. The potential due to the ring will be very easily you can calculate here. So now let us see the derivation now. So now see here this potential due to this ring for an axial point. So this ring we are taking here, the charge Q is distributed uniformly here, and we need to calculate potential at this point here. Potential at distance x from the center and x from the center here. So actually here we need to write, we can express this value as, suppose if I consider a small element here. So here if I am considering a small element, so then we can write this expression as actually the dV is equal to the potential at that point, we can write as K into dQ by, this element is at a distance of this under root of r square plus x square here. So that means we can write this as under root of r square plus x square, we can write this expression. And just integration of this element we need to write here. The integration of this element is nothing but integral of that means dv, integral of dv is equal to this k by under root of r square plus x square is a constant value, because here only the variable in case of this ring is only dq only. So the dq means we can write it as q. So that is nothing but what we are writing here directly, because simply you can simply in another way you can explain this as all the elements, if you are taking the different elements here, the distance of all those different elements from the point P is same only, under root of r square plus x square only you will get, because if you join all those elements here you will get similar to that of a cone. So every element of the ring will be at the same distance from that point P. So that the directly we can write this potential expression as potential at that point P is equal to 1 by 4 pi epsilon naught q by r square plus x square, we can write here. So this is a potential due to this ring at a distance x from this center on its axis. And now suppose if you want to calculate at its center means simply you can substitute x is equal to 0. If you substitute x is equal to 0, then we can write this as potential at the center, we can write it as k cube by r, we can write here simply. So that is potential at the center here, at the center of the ring, where k is at 1 by 4 pi epsilon naught value. So potential at the center is given by k q by r, we can write here, where r is the radius of the ring and q is the total charge distributed on this. So that is potential in case of potential due to a ring on its axis and at the center, right? So now with the help of this potential due to the circular ring, actually we can calculate the potential due to the disk. And this derivation is also similar to our previous derivations only. So let us see how to derive that. So now I am going to the disk. And so now here let us see here. Let us now find the potential at the potential at any point on the axis of a non-conducting charged disk having the surface charge density sigma. To find the potential, we can find the disk into large number of concentrics. So that means we know that to find the potential due to this entire disk, we divide the disk into small elements in the form of this ring. That element is in the form of a ring. So here actually the disk is of radius capital R here. This capital R is the radius of the disk. So now we are taking this small element here. So this is small element of so now this is our element what we are taking here. This is the ring element what we are taking. So that small element is of radius R. That small element is of radius R here. I think you got that what the element we are taking. So this is the small element we are taking here at a distance of that means from this center we need to find electric potential at this point here. So to write that, our procedure is same. First we write the potential due to this small element, and as our element is in the form of a ring, so we can apply simply the ring formula there. So before that, let us see how to write this dq value. Now up to now we discussed about the one dimensional or the linear objects. Now it's a two dimensional object here. So charge present on the disk we can write as dq is equal to sigma into area of this element we need to write. So area of element is nothing but we write it as 2 pi r into that circumference into width of this element. So that width of this element is nothing but a dr we can write. So 2 pi r dr will gives us area of this element here. So then for this just this ring element here, so we are writing the potential due to that ring element. So 1 by 4 pi epsilon naught dq by under root of r square plus x square we can write. Then just we are substituting the dq value here, then integration. The integration of this sigma by 2 pi 2 epsilon naught is a constant value. then integration limits are nothing but from r to 0 to r, because 0 means you will be at the center of the disk. So from the center to the edge of the disk we need to integrate. So that is from 0 to r we can write, capital R we can write. Now we need to integrate this, and this calculation also we did many times there. Like you can use a substitution method, like by taking x is equal to some r tan theta you may consider here by taking some angle theta here. So such a derivations also we did in the previous field calculations also. Then if you do all those derivations, that means all those calculations, here I am saying if you want to calculate you can do the further simplification. Just we use that equation as x is equal to, I can take this x is equal to, sorry, r is equal to x tan theta you can write by using this triangle. Just you may consider this angle as theta here. If I consider that angle as theta, then r is equal to x tan theta you can write. And from this you can write this dr value as x secant square theta d theta. And so just by taking this substituting these values here, you can do the further simplifications. Then you will get this expression here, sigma by 2 pi 2 epsilon naught into under root of r square plus x square minus x. So this is the potential at a distance x from the center of the disk on its axis. And if you are calculating at the center of the disk, if you want to calculate, then simply you can substitute x is equal to 0 in this equation, then sigma r by 2 epsilon naught you will get. So this is the potential at the center of the disk here. So you need to remember both the expressions. This is potential at a point on its axis, and you should also, this is just by substituting x is equal to 0 here, then you may get these expressions there. Potential at the center you may get. So that is potential at the center of the disk. And so now sometimes they may ask that potential at the edge of the disk. At some point on the edge of the disk they may ask. So let us see how to calculate potential at the edge of the disk. So now this is the potential at the edge of the disk here. If you want to calculate, say, potential due to this entire disk at a point here, this calculation is also important. So that means sometimes directly they will ask what is the expression for potential at the edge of the disk. And so then for this, let us see this derivation here. This is also same procedure. Even though our point is changing here, our procedure will be same. We write the potential due to the small element by taking a small element, and then we integrate that. Just by integrating that, you can calculate the potential due to the whole disk. So now here we are taking a small element here. So this is our element what we are taking at a distance of r from this. This is our point here. This is the point P where we need to calculate this potential. So then for this we are taking the small element here, AB. AB is our small element, which is at a distance of r from this. This is a circular arc element we are taking here. This AB is a circular arc of radius r centered about this point P here. And dr is the width of this element here. So now I am writing this charge on this element. So now charge on this element means we know this actually sigma into dA we need to write. So dA is nothing but area of this element we need to write. Just previously for the circular ring element we mentioned that when you in the disk, when you are taking a circular ring element, there we mentioned 2 pi r into dr, like length onto total length into thickness of that element we mentioned. So similarly here length of this arc we need to write. This angle is theta we are taking, so this total arc will subtend an angle of, if I draw this another line from here from point P to B, so then this angle will also be theta in this. So this angle will also be theta, and so that this total arc is subtending an angle of 2 theta here, and so that the length of the arc AB you can write it as 2r into theta. And so now 2r into theta into width of this element we need to write to get the area. So that is nothing but 2r theta into dr we are writing. So this is the total area of this element. Now we are substituting that element here and then integration. So then this is our 1 by this 2 we are cancelling here. So this is 1 by 2 pi epsilon naught into sigma into r d theta. So next let us see the simplification of this. So now to calculate this potential due to the whole disk, we need to integrate that expression. So we are writing it as V is equal to sigma by 2 pi epsilon naught into integral of theta into dr from 0 to 2r. And so now here the important thing here is this is theta and dr. That means we are integrating with respect to this dr, but here theta function is there, which is a variable there actually. And so now we need to convert this into two variables into a single variable. And so then we are converting this into theta. In terms of theta, we are converting here. So for that, we are writing this small r value. So let us see here in this triangle. So this is the theta what we mentioned there in that consideration. So just by using this triangles, we can write here. So this side is suppose I mentioned I am giving these names as so this is our point P. So this is our point B. Sorry, point A, that is. And so now this is another point I am taking here. So this is another point C we may consider. And so now this PC distance we can write as PC is equal to, here I can mention this value as PC is equal to CA, so which is nothing but R cos theta we can write by using that right angle triangle then. And so by using that right angle triangle, you can write this PC is equal to that CA, which is equal to, this is CA, which is equal to R cos theta we can write here. And so the total PA distance we can write that value as, so 2R cos theta we can write here. So now this is the R value, so we need to find the dr value here. So just I am differentiating this. So then dr is equal to 2R minus 2R sin theta into d theta you will get. And so then just by substituting this value here, that means by substituting this dr value here, we need to integrate this. And so then you will get this, if you substitute this dr value here, minus, I am writing this minus here. So 2r theta into sin theta into d theta you will get. And then limits will be from, you can observe this, limits will be from pi by 2 to 0 you will get. When you are at this point here, that means when you are starting from the P itself, that means when the point A and P are coinciding with each other, then the angle will be pi by 2 you will get, right? And when you are approaching this end here, and so then when you are approaching this opposite end, then you will get this angle as 0. The angle between this radius and this line here, PA line, that is the angle we need to identify here. When this point A reaches this diametrically opposite to point P, that means this point, then this angle between these two lines will coincide with each other. That means this PR line and this PA line will coincide with each other, so that the angle between them will become 0. So that here limits varies from pi by 2 to 0. That is the important thing you should note here. And then this integration, again here integration formula is required here. It is actually in integration product rule we need to apply here. So then product rule will be there here, and again if I mentioned here, but it is not required. Simply remember this. If you simplify this, you will get this total integration value as 1. And that means then you will get this sigma r by pi epsilon. That means negative sign is there, so minus 1 you will get. So finally you will get this expression here, sigma r by pi epsilon naught. The total integration by using this product rule I mentioned here, but it is not required. Once in mathematics, if it is completed for you, then you can solve that integration very easily. So that this is a calculation I mentioned here, which is not required. If you want to further go through that, you can go through that. That means if in product rule is completed in mathematics, then you can go through that integration calculation here. So this is a potential due to this disk at the edge of the disk here. So this important formula here, sigma r by pi epsilon naught, where sigma is the surface or density there. So it is the potential at the edge of the disk. And now let us take some objects like spherical shell or a solid sphere, volume charge distribution elements. So now let us see here electric potential due to a spherical shell. So here just we are taking a sphere, just I am drawing the sphere here. So for this sphere, first we are calculating the potential at a point outside here. So this is our point here. From the center, let us say this point is from the center we are taking here. From the center, let us consider this as at a distance of r from this. At a distance of r from this is P is our point here. This is suppose a center of the disk. And so from the center of the disk, we need to find the potential at this point here. So first we are finding this outside. So this is our outside case here. That means case 1 we are writing here. Outside the shell. In brackets you may write r is greater than r. So this is the case what we are taking here. And so now let us see here. Just we are writing the electric field outside this, outside the spherical shell here. This Q is the total charge distributed on this. Suppose we are taking that as a small q is the total charge distributed on this. And so now we are writing this electric field outside this 1 by 4 pi epsilon naught q by r. And actually directly you can also say by using our shell theorem, right? So we know that according to the shell theorem which we discussed in the gravitation, for an external point the shell will behave like a point mass placed at the center. And similarly here you can consider that as a point charge placed at the center. And so now here also we can take that directly. So directly you can write by taking the point charge simply, and just by using the EV relation I am going to explain here. So you can also directly write. If you are writing it directly, then 1 by 4 pi epsilon naught q by r directly you can say. No problem in this. That means directly by using the shell theorem you can say. So then just by using this EV relation I am going to explain here. So just if we consider this EV relation, so outside this 1 by 4 pi epsilon naught. Now we know the E expression minus dV by dr. And so now just that expression we are substituting here. So then just by writing this term this side, then just integration. And we integrate from infinity to r. So infinity potential is 0. So 0 to v you will get. And just by integrating this minus, that means 1 by and r square integration, then you will get this finally and substituting these limits infinity to smaller, then finally you will get this. So which is nothing but our point charge. So directly you can mention it as by shell theorem. For this shell, according to the shell theorem, you can mention this as this will behave like a point charge here. So this will behave like a point charge placed at its center. So you can directly consider like it is point charge is placed here at this point, and we need to find the potential at this point, which is at a distance of r from this. Then directly you can apply this formula here, that 1 by 4 pi epsilon naught q by r formula directly we can write. That means from outside, now we can mention this outside it is inversely proportional to r. So this is a field potential outside. And whereas suppose say on the surface if we consider here, so this I am taking it as a now case 2 on the surface. On surface. So on the surface if I consider here, I can mention it as simply you can substitute this small r is equal to capital R on the surface means. Then 1 by 4 pi epsilon naught q by r you will get. And whereas suppose if you want to write the inside, so that means now that is our case 3 here actually. So inside if I mention, so inside means now we may consider like if you are writing this inside here electric potential inside. So first let us write electric field inside. So electric field inside is 0, right? So electric field inside the spherical shell is 0. So electric field inside the spherical shell is 0 means according to our EV relation, I can mention this as dV by minus of dV by dr is equal to 0. So dV by dr is equal to 0 means we can mention that V is equal to a constant value. Because we know that when differentiation of a function is 0, then it must be a constant, that function may be a constant function here. So here it is a constant function, and constant in the sense its potential is not changing when you are traveling from surface to the inside. And so whatever the potential is there on the surface, the same potential will be there inside also at any point. So inside also that potential is given by this inside potential is same as that of surface potential. So 1 by 4 pi epsilon naught q by r we can write here. So that's the important point you should note regarding the shells. Regarding the shells, at any point inside is same as that of the potential on the surface. Is it clear? At any point, potential inside the spherical shell is same as that on the surface. There is no change in the potential inside. It will be a constant value. And whereas outside means, as we mentioned, then it is q by smaller you will get here. And so that variation of potential with the distance, now we can mention like this. By the graph we can draw like this. So when you are traveling from center to the surface, this potential will be a constant value, which is 1 by 4 pi epsilon naught q by r you will get. And whereas outside it's a rectangular hyperbola because it is inversely proportional to this r. These graphs are very important. Field graphs and potential graphs due to the spherical shell and a uniform charge distribution, solid sphere. So this is for this uh, shell, variation of potential due to the spherical shell. Is it clear? So all these derivations are simple only, very easy derivations only, because we did such a similar derivations for the recently for the field, similar, not exactly same, but the similar derivations. And then we did all these potential calculations also in the gravitation topic, and so that all those derivations will be easy for you all. So you can easily understand all those derivations. And next here, electric potential due to uniformly charged sphere. So uniformly charged sphere in the sense this charge will be distributed throughout this volume inside this sphere also. It's a non-conducting sphere here. So throughout this charge will be distributed here. A charge Q is distributed throughout this. So then outside means here also directly for this also you can directly write by using our say point charge, that means shell theorem. For external points, because for external points shell and solid sphere will behave like a similarly only, because simply we can say the simple logic by seeing just from outside you can't decide it whether it is a shell or a solid sphere. So for behavior of shell and solid spheres will be similar for the external points, whereas for the internal points the both are differently and both are different behavior will be there. And so now for the external points again directly you can write by using shell theorem. So here also just I am taking this E expression and from this I am going to derive here. So then E outside we can write as 1 by 4 pi epsilon naught q by r square. Now again we are using the dV relation. So from this dV is equal to minus E into dr you can write. And we are integrating this expression here. So again from infinity to r. So then 1 by 4 pi epsilon naught q by r square, then infinity to r you will get. So exactly same as that of shell you will get here. So that shell is nothing but V is equal to 1 by 4 pi epsilon naught q by r you will get. Even for the solid sphere also you will get the same, which is same as the point mass also. That is nothing but what I said. You can also apply the shell theorem directly, so that you can say it as a directly this point charge expression you can write here, right? So that means now we can write this as V is inversely proportional to R for an external points there. And so next let us write at a distance, that means on the surface. On the surface means simply as similar to that of shell. That means for shell and the uniform charge distribution of solid sphere, both the cases will be first two cases. That means first two cases in the sense outside and on the surface. Those two cases will be same only. The only difference will be there inside. When you are writing the field or potential inside, then both the behaviors will be different. And so then on the surface means again we can substitute this small r is equal to capital R. So V is equal to 1 by 4 pi epsilon naught q by r you can write. Then this is the potential on the surface of the solid sphere. Next let us write inside. And so now this important calculation, and you need to remember this expression here. So now this inside you can write it as our formula for the field inside. So we are taking at a distance of r from the center. So at this point we are writing here. So this is our point, required point. Say that this is the point P here. So at this point we are going to write about this potential. So then we are writing the field at this point here, 1 by 4 pi epsilon naught q by r cube into r, which we derived already. Again we are using this EV relation, and then we are integrating here. And now here you can observe this. I am integrating from the surface to V. That means potential between these 2 points I am taking here. From surface to the point P I am taking here. And so that here the limits also I am taking from R to smaller. You may also consider it from infinity to R. When you are writing from infinity to R, then here the limits will changes from 0 to V, because at infinity potential is taken as 0. But if you are taking from infinity to R, here calculation you need to involve the two steps, because this is a field inside. When you are traveling from R to R, field variation will be in one way. When you are outside, the field variation will be another way, like 1 by 4 pi epsilon naught into q by small r square you will get. Outside means, inside means this expression you will get here. So instead of taking those two steps, I am taking it as a single step here, so that I am integrating from surface to this point only. Because potential at the surface, just now we already calculated in the previous case, that means in case 2. We already mentioned the potential on the surface. So just we are integrating from this capital R to small r, that is from surface to the point P here. And so that's why I am taking this limits as from Vs to V. And so that here it is from R to R. So just here integrate this, and then you will get this 1 by 4 pi epsilon naught q by R cube into R square by 2 you will get, and this is from R to R. Just substitute the limits and then substitute this Vs value. Potential on the surface of the sphere is given by 1 by 4 pi epsilon naught q by capital R you will get. So just by substituting, then you will get this expression here. So that generally we write those expressions as, so generally let us say this, generally we write this expression like this. V is equal to 1 by 4 pi epsilon naught into q we are writing outside. So then 3r square minus r square by 2r cube. So that means in general, in terms of k, I can mention this expression as, we write this expression as V is equal to k into q by 2r cube into 3r square minus small r square. That means generally we express this expression like this, just that k value I mentioned here. So this is the potential due to the uniformly charged sphere at a distance r from the center and inside the center. This is an important formula, and you need to remember this formula, because if you remember this expression, then only you can solve some problems here. Whenever the problems are there starting from this inside this solid sphere. So if the charged particle is starting from, or whenever it is moving inside the solid spheres, then we need to remember this expression here. So this is important expression only. And we now justify, substitute this at small r is equal to 0. Small r is equal to 0 means at the center of this solid sphere. Then you can substitute small r value as 0 here. Then you will get 1 by 4 pi epsilon naught 3q by 2r you will get. So whereas 1 by 4 pi epsilon naught q by r is nothing but potential on the surface. So potential at the center will be equal to 3 by 2 times the potential on the surface. So sometimes this is also important relation only, potential between relation between potential at the center and potential at the surface. So sometimes I will ask this ratio here. So potential at the center to potential at the surface ratio. So which is nothing but 3 by 2 we can write there. So that is another important relation here. So potential at the center will be the maximum value. And so now if we draw the variation of the potential with the distance, then you will get the expression like this, right? So this is maximum value potential at the center. So when it is moving from center to the surface, then its variation will be like this. According to this equation, you will get like parabolic curve you will get. And whereas outside is, it is inversely proportional to r you will get here. So this rectangular hyperbola part you will get. So you should remember potential will be maximum at this center of this spherical shell, uniformly charged sphere. And this is a variation of this potential here. So that means in order to solve the problems, you need to remember all those expressions. If you know the formula only, you can solve those problems. Like we solved some problems in the previous field topics. So based on the field topics, lot of problems we solved there. If you know the formula, then only we can solve that problem there. So similarly here regarding the potential also, if you know the potential formula, then only we can solve that problem. So it is better to, that means all of you should maintain a separate formula list. So by this weekend, you have to post all the formula list to me. That means from the beginning of this electrostatics, whatever the formula, important formula are there, write the formula list as a separate, and so that means maintain the separate list for that throughout this in any topic, or just a completion of that weekend before going to writing that weekend examination. You have to prepare the formula first regarding that topic there. Then you can easily solve the problems based on this. So now let us say this potential due to the